We need a electromagnetic wave to see the object. There are two ways to observe the object. One way is to see the object by detecting the electromagnetic waves reflecting from the surfaces of the object. This is how our eyes see the object. Our eyes collect the visible light reflected from an object surface, and the brain uses this light to create an image. The other way is to see the object by detecting the electromagnetic waves which are transmitted through the object. In the X-ray CT, by detecting the transmitted X-ray through the body, the inside of the human body can be seen. On the other hand, in the transmitted electron microscope, an image of the inside of the object is created by using the transmitted high-speed electrons. The diffraction phenomenon of the wave restricts the resolution in observing an object. This resolution roughly corresponds to the electromagnetic wave's wavelength. The optical microscope uses a visual light, and its highest resolution is 0.5 micrometers, which is average wavelength of the visible light. Thus, the magnetization of the optical microscope is about 2000. We can significantly improve the resolution of a microscope by employing high-speed electrons. Quantum physics states that the particles should be regarded as a wave, with a wavelength that is inversely proportional to its velocity. By applying high voltage, we can accelerate the electrons and reduce their wavelength. We employ extremely fast electrons in the electron microscope to see an object. This lecture explores the basic principles of the electron microscope, which has a significantly higher magnification than an optical microscope. The coronavirus and other much smaller objects that the optical microscope cannot see can now be seen with this electron microscope. As seen in this figure, the coronavirus is around 100 nanometer in size, which cannot be seen by optical microscope. But we can observe this coronavirus using the electron microscope. Let's first see the optical microscope's magnification limit. Diffraction causes the image formed by the lens to deviate from the object itself. The image of a point object, so point source, through a lens, for example, is not a point but rather spread out due to diffraction. Consider the images produced by the lens of two point objects A and B is shown in the figure. There are two objects here, and this is lens, and image is formed here. The lens, let's say lens of the eyes, spreads the image of two point objects in the image plane. So, retina here. So you can see this eye, and this lens of eye and the retina here. If two objects are separated by a large distance, these two objects are separated by a large distance, then the images of two objects can be distinguished in the image plane here. If two objects are close together, however, the images overlap and are difficult to distinguish. So this image shows when the two objects are separate large distance, so we can see clearly there are two objects. However, two objects are getting close together, then images of two objects also getting close together, and we cannot resolve whether there are two objects or not. The Rayleigh criterion, which defines the limit for distinguishing the image of two point objects formed by lens, states that if the maximum of one image is close to the minimum of the other, the two images cannot be distinguished. So here, this red image is due to the object B, and blue image is due to the object A. And here, the maximum of one image, for example, this red image, so this maximum here. So maximum of one image is close to minimum of the other, blue, so minimum of the other. And let's close more than this point, then images are getting closer and we cannot distinguish these two objects. Okay? So Rayleigh criterion states that if the maximum of one image is closer to the minimum of the other, closer than this, then the two images cannot be distinguished. Okay. This criterion can be obtained by using diffraction of electromagnetic waves. We cannot mention this in details because it's a very complicated mathematical approach. We need that, so we cannot discuss that here. But the result is given by this equation. So final outcome for Rayleigh criterion is given by this equation. Theta minimum is the angle viewed from lens to the objects, this angle, and lambda is the wavelength of the light, and d is the diameter of the lens, the size of lens. I wrote this again here. The diameter of the lens and that's the wavelength of the light, lambda, are represented d and lambda respectively, while the angle of two objects to the lens is given by a theta. Here theta minimum is the angle between two objects viewed from the lens that must satisfy the Rayleigh criteria. Let's see some example here. Let's figure out the minimum distance between two objects that the lens can distinguish. This is a satellite orbiting around Earth. Assume we are looking at the Earth through a lens with a diameter of 20 centimeters mounted on a satellite 5 kilometers above the surface of the Earth. In this case, above equation, this equation can be used to calculate the minimum angle viewed from the lens to the two objects on Earth. So there are two objects separate by a certain distance, and your angle theta minimum is the angle for Rayleigh criterion viewed from lens to the two objects, the theta minimum. We can calculate this theta minimum because we know that d is 20 centimeters, and lambda is the wavelength of visible light, that is average wavelength of visible light is 550 angstrom. So we can use that number here, then we can obtain theta minimum 3.10 to the minus 6 radian. Using this relation, x minimum equal s. S is the distance between the satellite and the object, so 500 kilometers. So the minimum distance between two objects on Earth that can be distinguished by the satellite lens is calculated to be 1.5 meters. Okay. This means that if two objects on Earth are distanced by more than 1.5 meters, the satellite lens can distinguish them apart as two distinct objects. On the other hand, two objects are closer than less than this 1.5 meters, then this lens on the satellite cannot distinguish two objects. Due to diffraction, there is a minimum distance between two objects on Earth that can be distinguished as two separate objects by a satellite camera. The angle between these two distinguishable objects as seen via lens is theta minimum, this relationship. To magnify a small objects, an optical microscope is utilized. As illustrated in the figure below here, it consists of two lenses, the object lens and the eyepiece. The basic principle of a microscope is that the object is set in front of the objective lens is focus. Yeah. That is objective lens, and the objects is put in just the front of the object lens focus. Here, object lens is focus here, and just outside of this objective lens focus, the object is located. And then the first image is formed inside or at the focus of the eyepiece, resulting in a large final image. So first image is formed inside the focus of the eyepiece. Here is the focus of eyepiece. So first image, this is first image. So first image is formed inside the focus of the eyepiece or at the focus of the eyepiece. Then final image, this final image can be seen from by our eyes. It's very large. A final image can be seen by our eyes. The final image is constructed at infinity if the first image is formed at the eyepiece's focus. If the first image is formed at the focus of the eyepiece, then final image will be formed infinity. Okay. If the first image is formed at the specific position inside the focus of the eyepiece, shown in this figure, the final image can be produced at the near point of the human eyes, about 25 centimeters in front of the eyes. So this figure shows this final image. The distance between the objective lens and the eyepiece is given by t. T is sum of f0, L, and Fe. The focal lengths of the objective lens and eyepiece, as well as the distance between their focuses, are represented by Fo, Fe, and L respectively. So Fe is the focal length of the objective lens, and Fe is focal length of eyepiece, and L is the distance between focal length focuses of objective lens and eyepiece. The effective focal length of two lenses separated by a distance d can be calculated as follows. We can calculate the effective focal length of two lenses separated by distance L by using this equation. So F4 is the focal length of the objective lens, and F is the focal length of eyepiece. And these two are separated by distance d, so we can get the effective focal length of these two lens system separated by distance d in this equation. As a result, the microscope's magnification is expressed as this relationship. The above magnification is based on the final image being formed at human eye's near point, 25 centimeter. The final image is at infinity if the first image is formed at the eyepiece's focus. In this case, the above magnification is changed to this relationship. +1 is different, right? According to the above equation, the magnification of the microscope is the product of the magnifications of objective lens and eyepiece. So the product of the magnification of two lenses. So this is magnification of objective lens, and this is a magnification of eyepiece. So product of two magnification gives the magnification of the microscope. This shows the Rayleigh criteria. Two objects are close, then this Rayleigh criteria, we cannot distinguish two objects. How to distinguish the two objects? The microscope's maximum magnification is limited by diffraction. The distance between the object and the lens, eyepiece in microscope, is the focal length of the eyepiece in the microscope. Since the first image in the microscope is formed at the focus of the eyepiece, so here we can compare these two figures. This corresponds to eye, and we have two objects here, and the distance between objects and the lens is r, and here object is here and the lens is here, so r corresponds to Fe here, and the first image, this first image is formed at focus of the eyepiece, so focus of nearly close to focus of the eyepiece. So in this figure, R corresponds to Fe here in this figure. So we can set R equal to Fe. As a result, the microscope's minimum distinguishable distance x minimum between two objects is expressed as R theta minimum. So theta minimum is given by this relationship, and R is Fe here. We assume then we can have the lambda x minimum is nearly close to lambda here we assumed that the value of Fe over D over Fe is close to 1.22, so we can cancel out this 1.22, then we have the number. In this case, we assume that this is close to 1.22, then we have the x minimum, the distance between two objects, observable, distinguishable distance between two objects is nearly the same as the wavelength of the light we used. If the final image is less than 1 millimeter in size, it appears blurry to the naked eye or on the image film. As a result, microscope's maximum magnification is given as this relationship. So H prime is close to 1 millimeter, and wavelength of visible light, the average wavelength of visible light is 550 angstrom, so we can put a number here. Then finally we have maximum magnification of optical microscope is about 2000. Okay. Here we use the wavelength was taken as average wavelength of the visible light, 550 angstrom. Now let's see the electron microscopes. The basic function of a microscope is to collect light reflected from an object and construct an image much larger than the object using this collected light. The lens in an optical microscope collects the visible light reflected from the object. The magnification of a microscope is determined by the wavelength of the light used for imaging, as shown above. The maximum resolvable size of the object in the optical microscope was the wavelength of the visible light. As a result, we realized that the wavelength of the light should be as short as possible in order to enhance the microscope's resolution. The electron microscope uses high-speed electrons instead of visible light, which is used in the optical microscope. The electron microscope has been developed and improved since the 1930s in order to obtain a higher resolution than the optical microscope. High-speed electrons are fired at the objects in an electron microscope, and the image is created by collecting the electrons refracted from or transmitted through the object. The object's electrons are collected by the magnetic lens. Let's see the electron gun. The wavelength of matter at the speed of v is given by the Broy's matter wave as h of mv, where m is the mass of the electrons and h is a Planck's constant. The figure depicts the electron gun structure. This figure. If the voltage V accelerates the electrons as indicated in the figure, the energy relationship of EV equal half mv square yields the electron's speed. And The wavelength of the electrons is given as this relationship. If we put the speed v here, we can get this relationship. The wavelength unit in the equation above is angstrom. This lambda in units of angstrom. The de Broglie wavelength of the electrons is about 0.4 angstrom if a voltage of 1000 volt is used here. If these electrons are used in a microscope, the object's resolvable size is also about 0.4 angstrom. However, since various drawbacks should be considered, and thus the resolvable size of the object is somewhat larger than this theoretical value. In the electron gun, this heater, and this is metal. Heater is on, then due to the heat energy, the surface free electron of the metal will come out, and these electrons are accelerated by this voltage. Okay? So the metal heated by the filament emits free electrons that are close to the metal surface. A high voltage V then accelerates these electrons. Now let's see first the transmission electron microscope, TEM. The transmission electron microscope has a structure that is nearly identical to that of the optical microscope. Visible light is used to shine the object in an optical microscope. On the other hand, high-speed electrons are transmitted through the object in the TEM. The visible light refracted from an object is collected by two lenses, objective lens and eyepiece, in an optical microscope, and the image is formed by these collected lights. On the other hand, the electrons transmitted through the object in the TEM are collected by the magnetic lens, objective lens, and eyepiece, which is basically a magnet. Since electrons are charged particles, the magnet can't control their paths. The TEM magnification ranges from 50 to 1 million. So electrons will pass through the sample, and these transmitted electrons are collected by magnet, and these electrons will be collected on the film or CCD to give the TEM image. And inside the TEM, the high vacuum should be maintained because electrons is moving inside the tube, and so there should be no gases inside. So high vacuum should be maintained here inside. This figure shows one example of TEM, and the magnification of this TEM ranges from 50 to 1 million, and the resolution is 1.4 angstrom. And this figure shows the TEM image for nanoparticles. The size of nanoparticle is about 100 nanometer. And this here shows the time image of coronavirus, and also the size of this coronavirus is about 100 nanometer. Now let's see a scanning electron microscope, SEM. The scanning coil, this one, of the scanning electron microscope moves high-speed electron beams across the object surface. So using scanning coil, we can move the electrons across the sample. Then the secondary electrons are emitted when electrons hit the object surface, and these scanned secondary electrons can be used to construct object image. The SEM has a resolution of around 10 to 200 angstrom, which is low in comparison to TEMS. TEM case resolution is 2 to 5 angstrom. The preparation of the sample in the SEM, on the other hand, is relatively simple, and the scanning coil can recheck the object image of the uncertain region. The image can be obtained in the TEM by transmitting electrons through the sample, and thus the equipment must be reset for the new image. But nowadays, the scanning TEM was developed, so we also recheck the uncertain region using SDM. As a result, the SEM is widely used despite the fact that its resolution is lower than that of TEM. The SEM's magnification ranges from 10 to 300,000 times. And inside tube here, high vacuum should be maintained as in the TEM. This figure shows one example of SEM, and its magnification ranges from 10 to 300,000, and the resolution is 15 angstrom. This figure shows some examples of the SEM images. A mosquito head, 200. This is magnification. Mosquito head 1000 times, and diatom 5000, and moth 15,000 magnification. Next, let's see the scanning tunneling electron microscope, STM. The scanning tunneling electron microscope, STM, makes use of the quantum mechanical tunneling effect. The tip of the probe in the figure has an angstrom order diameter, which is equivalent to the size of the atoms. So diameter of this tip is very small, just 1 angstrom in diameter. This probe scans the sample object at a distance of 10 angstrom above the object surface. If the probe's tip is at this distance from the object, electrons from the object can tunnel through the vacuum to the tip when a small field is applied across tip and the object. So if we maintain the distance between this tip and the sample surface 10 angstrom, then we apply some electric field across these two tip and the surface, then tunneling electrons are emitted from the metal surface to the probe. So in order for the tunneling effects to occur, the tip must be close enough to the object surface. If the distance is greater than 10 angstrom, the tunneling effect does not occur. The feedback circuit of a piezoelectric transducer can control this distance. As a result, the tip follows the prominence and the depression of the object surfaces, and the movement of the tip can be used to construct an image of the object surface. So the electrons in the metal, so we have to use metal surface, otherwise the tunneling electron will not coming out. So the electrons in the metal are ejected by a small voltage across the tip and the metal surface by quantum mechanical tunneling if a very sharp tip of angstrom order is moved close to the metal surface by about 10 angstrom. This slide shows some example of the image of STM. The tip of probe in STM is very sharp, so less than angstrom in diameter, so we can pick up the atoms by using that STM and move that and to the some plate of and rearrange the atoms. So this figure shows using FTM 48 the iron atoms were arranged in a circle with a radius of 17.3 angstrom on surface of copper. So these iron atoms and 48 iron atoms are arranged on the surface of the copper, and the radius of this circle is 17.1 angstrom. This figure also shows the xenon atoms are arranged on the nickel surface. The letter IBM is made by xenon atoms on the nickel plate. And this figure shows iron atoms arranged on the copper surface, and this letter, Chinese letter, shows the atom. This figure shows carbon monoxide molecules are placed on the plate of platinum, and something like human. So arrange the carbon monoxide atoms to make some kind of the human shape on the platinum surface. The STM has a horizontal resolution of around 1 angstrom and a vertical resolution of about 0.1 to 0.01 angstrom. As a result, an image of less than atoms can be generated. The STM can only be used on metals. There is no tunneling effect between tip and insulator, so we have to use the metal sample, otherwise we cannot have the quantum mechanical tunneling electrons. This figure shows STM image of silicon's 111 surface. And this image shows the hexagonal honeycomb structure of the graphite lattice. And the distance between the atoms is 0.5 nanometer. Now let's see the atomic force microscope, AFM. Since high-speed electrons are not used for imaging in this AFM, so the electron force microscope is not an electron microscope. The purpose of this microscope was to image the surface of insulators. As previously stated, the STM can only be used on metals. The atomic force between the tip and the surface atoms of the object is used to image the object in the AFM. Benning and Rohrer developed this AFM in 1981. The AFM is now frequently utilized to image both metal and insulator surfaces. This is the tip of the AFM, and this figure shows that's a silicon tip, the silicon tip of the AFM. And in this figure, the surface of the tissue type transglutaminase coated on the mica. The cantilever is used to scan the surfaces of the sample object in an AFM. This is cantilever. The cantilever in this case is a crossbeam with one end fixed and the other end free to move. So one end fixed, the other is free to move. The free end is equipped with a silicon or silicon nitride tip, diameter less than 100 angstrom. There are several forces at work between the tip and the sample object's surface atoms. These forces are affected by the distance between tip and the object, as well as the material of the object. There is repulsive force at the point of contact, van der Waals forces at the distance, surface tension, magnetic force, Casimir force, electric force, and solvation force, etc. The above forces bend the cantilever when it is close to the sample object. The laser and position-sensitive photodetector are used to measure the bending. So this bending is measured by the laser and the photodetector. If the cantilever is bent by delta H, during the scanning process, the reflected laser beam from the cantilever surface is slightly displaced. As shown in the figure below, the photodetector measures this displacement, delta H. In this case, delta H is increased to become delta large H during this process. Okay. Due to the cantilever's interaction with the sample surface, the cantilever is bent. It follows that the laser and the photodetector will magnify this bending. These measurements can be used to construct the sample surface irregularity. The piezoelectric transducers are mounted to the cantilever for tip scanning. Transducers are divided into two categories. One is used to scan the sample object's horizontal surfaces, XY surface, while the other is used to scan the vertical direction. The position of the cantilever can be changed by applying voltage. Contact, non-contact, and the tapping modes of operation are available depending on whether the cantilever is contacted by the sample surface. The tip drags the sample surface in contact mode to detect the prominence and the depression of the object surfaces. This method is no longer used since the sample surfaces can be damaged in this mode. In non-contact mode, the tip vibrates at the cantilever's natural frequency, scanning the sample surface. The tip does not make touch with the sample surface in this case. The van der Waals force between the tip and the atoms of the sample surface varies with the scanning position, change the vibrating frequency of the cantilever. For the solid sample, we can get the same images in both contact and non-contact modes. The non-contact mode, on the other hand, cannot see the surface underneath the fluid layer if it is observed on the solid surface. The tapping mode was developed to solve this problem. During scanning of the sample surface, the tip taps the sample surface in this mode. In this process, the tip vibrates at the natural frequency of the cantilever. The surface beneath the fluid layer can be seen in this tapping mode.